I guess we stopped in the middle of this problem. Let's see here. Okay, so real quickly, just want to review the particle motion that we did at the end of last class. Okay, so remember when we originally did displacement and, you know, when something was moving to the left or to the right, usually I would give you position and you would do the derivative, right? And then we would do the number line. So what's different about these problems, I'm giving you velocity. So you don't have to do the derivative. You go right to just setting up the number line for left, right, and when it stopped. Okay, and then particle displacement. Well, if you have position, how do you find displacement?
Find the integral.
Oh, no. If you have position, it's the end position minus the initial position, right? Okay. So if you have velocity, right, you don't know what the position function is, so you apply the integral to the velocity function, right? And then you get basically your position at the end minus position at the beginning. And then, what else do we have? Oh, final position. So that's initial plus your displacement. And total distance traveled, we want to make the absolute value. Because we want to count when we go left or right, always as positive. Okay, so we stopped at B. So particle displacement. And then I think I also talked about, like, when we integrate, there was a shortcut. So anytime the derivative of the inside is a constant, you're going to do the antiderivative of the outside, and then keep the inside the same, divided by the derivative of the inside. Okay. What? All right. So we have to evaluate this. What do we get when we evaluate? When do we have to do? So anytime I have, let's say it's cosine of 2x dx. This is really a u substitution, but a quick way to do this, right? If I take the derivative of the inside, I get a constant, right? Derivative of 2x is 2. So if that is the case, I can use a shortcut, which, what's the antiderivative for cosine? Is it positive or negative? Positive. So it's sine of 2x, and then you just divide by that derivative of the inside. And then that would be a plus c. Okay? So if I have e to the 4x dx, what would that be? It would be e to the 4x divided by 4. Now, when I get into more complicated type problems, like, I can't use that rule anymore. Because what's the derivative of x squared? It's 2x. So I can't apply that rule to this one. Okay? That one we'd have to go through the u substitution. So we're okay with how I got this? And now what do we want to do? We want to plug in pi over 2, evaluate, and then plug in 0. What do we get? We get 3?
No, I don't.
You're just like making things up? You just get 3. Well, let's... So, if we plug in pi over 2, what's cosine of 3 pi over 2?
It's 0.
Thank you. It's 0. So we have 0 minus... Oh, it keeps doing that. I don't know. Sorry. What a great Monday start. It feels like a long time. Okay, I hope it doesn't flip. So it's going to be 0, 0 minus negative 2, so we get 2. Yeah, well, somebody can clean it. What is the final position? No, okay. If S of 0 equals 3, so that means when t equals 0, so the starting position, we're already starting at a position of 3. Yeah, so I add what my displacement is, and I get, yeah, so it's going to be 3 plus 2 equals 5.
Why is it 3 plus 2?
So we started at a position when t equals 0, initial position is at 3. Okay. So the particle starts out at 3, and then the displacement is 2. So we add those two together. Okay? Are we all right with that? And then what the last part is the total distance. So for C, how do we find total distance? Right. So we're going to do, now we don't care, total distance traveled, we don't care where we started at. Okay, we just care about the particles, basically how much it's traveled from 0 to pi over 2. So we want the absolute value of 6 sine 3t dt. And is it?
It is not.
Let's use our
Because
calculator.
From 0 to pi, from pi over 3 to pi over 2, it's going to be negative, so you have to do that.
Remember, if you think of the sine curve, right, 6 sine of 3t, it's going to have some parts above and some parts below the x-axis. So that means, remember, this is velocity. So every time velocity goes below the x-axis, that means our particle is going to the left. It's going in the negative direction. Does that make sense?
Yeah.
Yeah?
So you're just going to graph that?
Sure.
Well,
And see where
We'll
it
just
crosses
go-
the x-axis?
we can. I'm just going to put in. We could look at a few different options. I'm just going to plug it into my calculator to start.
Will this be a calculator okay problem?
Yeah.
You want the AP test?
Okay, so I'm going to show you, I showed you previously. This could potentially be a no calculator problem.
Interesting.
So this is where, I think, Gilad, you were just saying, like, where is it going to be positive? Like, if you think, what's, here, takes from 6. Yeah, what does this mean? So, what's,
you divide it because it's the whole period thing.
right, so what's the period for this sine function? 2 pi over 3. It's been a while, huh, guys?
Halfway through and go switch from positive to negative, so it's pi over 3.
Right. So if you had to do this by hand, which it would be more like this one.
Yeah.
Do you remember this one that we did? It's coming in. Okay, so when we did this one, we did this one, 24 minus 3t. We talked about, based on the number line, we know it's going to be positive from 0 to 8, and then it goes negative from 8 to 10, right? So I can break it up from 0 to 8, do that, because that's going to be positive. But what happens with this area, it's going to end up being negative. So whatever we get for this, we just make it positive. Does that make sense? So now we already did the number line. You see this? So from 0 to pi over 3, it's positive. And then from pi over 3 to pi over 2, it's negative. Now you could also look at the graph by doing, right, but we already did this work. So what's that mean? That means from 0, we could break this up into 2 separate integrals. Exactly. So I'll just write it out. So from 0 to pi over 3, it's just going to be 6 sine of 3t dt. And then plus, and we just want to take the absolute value, same integrand. It's just this one, when I actually figure out that part, it's going to end up giving us a negative number. We just want to make sure it's positive because we want to take, it's kind of like looking at the area under the curve, but it's actually total area. So when it goes below, we want to count that as a positive. And what did we get, just to save time here? 6. You guys should know how to do this by hand, right? Okay. No? What's wrong? Well, just like what I was showing you here. And then you just have to evaluate. Okay. All right, here, example 3. Car is moving with initial velocity 5 miles per hour and accelerates at the rate of 2.4 t miles per hour per second for 8 seconds. So how fast is the car going when the 8 seconds are up? Any ideas?
What if you just take the acceleration, multiply by the number of seconds, and then add 5?
So, look at this. Sorry, I just need to see if we
You have to take the derivative.
Well, hold on. How fast? What is this asking about? How fast? Okay, that's velocity, right?
So you have to take the integral.
We'll say the final velocity. Okay, what is the final velocity? That's really what we're asking. After the 8 seconds are up, right? So remember how when I gave you velocity and I said, well, where's the final position? Right? We did the initial position plus the displacement, right? Okay, so now I'm giving you acceleration, and we want to figure out working backwards to get the velocity. Does that make sense? Okay, so I want to figure out, how would I do that?
Velocity equals the integral of acceleration.
Okay, now, there's actually a couple different ways that we could do this. Yeah, so here's, I'll show you two different ways of thinking of this. You agree with that?
Yeah.
Velocity is going to be the integral for your acceleration. So what would that be? It's 2.4
squared over 2.
over 2, right? Plus c. Now we know v of 0 equals 5. So I can figure out that c is equal to 5, which some of you may have already guessed because that was your initial plus, right, the change in velocity. So plugging in 5 here, I get c equals 5. So I know my velocity function is what? 1.2 t squared plus 5.
And how would you know that it was going to be 5?
If v of 0 is 5. So when I plug 5 in here and make t equal to 0, I get c equals 5. Does that make sense? So now so by plugging that back in, right, now I have a velocity function. So now I can say, how fast is the car going when the 8 seconds are up? What do we do? So we plug in 8 seconds, right? 81 point. Okay.
On the AP exam, if it's a decimal like that, do we need to add zeros to make it 3 decimal points, or is that fine?
If it just automatically rounds to the 10th or the 100th place, then you don't need to put extra zeros for placeholders. That's fine. Okay, so the other way to think of this, just by the way, right, we wanted to find the velocity at 8 seconds. So if we do v of 0, which is your initial plus your displacement. Oops, that's supposed to be an A. It's just, right, that's what we were using from the previous page. It's just we're applying it to acceleration now. This would, basically this gives us this answer. The additional piece that we actually came up with the velocity function. So how do you have to do it? Doesn't matter to me. They're both correct. Okay. Now, how about B? How far did the car travel during those 8 seconds? How far? So now we're answering total distance traveled. Right? That's not an issue here. I'll put it in absolute value, but we'll see that we don't need it. So total distance traveled, what's the total distance? That's the... Well, we already found, remember how we found velocity here?
Oh, I get it. Never mind.
We're good?
Yeah.
Okay. Kind of running out of room here. Right, and what Bess was saying, this isn't negative anywhere, so you can actually drop the absolute value if you want and just integrate. What do we get for that? Just, again, you could use your calculator just to save some time. Anybody have their calculator? I have mine, but... Or you could just do it by hand. It's not that hard.
No. Never mind.
Could you just do 81.8 times 8 over
Yeah, just one. Hold on. Did you get 244.8?
Yeah.
Okay, so we have...
I don't know why.
No, that's fine. We got an issue here. This is not the right units. Okay. So notice that this was miles per hour, and we were integrating with respect to seconds. Oh, I still have it frozen. Sorry.
Oh, so that's the correct answer.
So if we have 244.8, we have to convert that.
So 0.068.
0.068? Yeah. I think I'm going to have to start using a different program here. It keeps... What? I know, but there's a reason that I ink on the actual Word document, but... No, I actually did freeze it. I was just checking something. But I'm having also other computer issues. It's like... It might be, but it's kind of annoying. Okay. So remember, this was miles per hour, and the units were in seconds. So what we have to do is we have to divide by 3,600, because that's how many seconds are in an hour. So we get 0.068 miles. You can also change that into feet by multiplying by 5,280. Okay.
How do you know that it's in seconds? Yes.
You want to change? Okay, so here's the thing. If you wanted to change the 8 seconds right from, like, if you don't want to use your, well, this would still be 0. But if you want to change that to reflect how much of an hour, you see this is miles per hour, so if you want to change that to hours, that's fine. It doesn't matter. It doesn't matter if you change it at the beginning or the end. It's the same. Because remember, multiplying by a constant doesn't affect, doesn't change anything with how you integrate. All right. We just have 2 more, right? Oh, no, we have another page. Yeah, sorry. I forgot about that other page. We'll still have plenty of time to finish. Okay, so here is, this would be a calculator problem. So what are we given here?
Limits.
Okay, so the first thing you want to do, so when you're given a graph or a function or a table of values, and this is going to be really important when you do free response questions, is look at what are we starting with. Sometimes we're starting with position, sometimes we start with velocity, sometimes we start with acceleration. So that last problem, we started with acceleration, right? And we had to work backwards to find velocity. This one we're given velocity, and we're also given the graph. Okay? And we want to describe the motion of the particle. What do we need to do?
Total distance and displacement.
Don't even need that.
That's the graph of the velocity.
This is the graph.
Velocity is negative, it's moving left. It's positive,
Yeah.
it's moving
So all we really need to do
It's fine.
is find that point and make a number line. Okay, this is not intended to be a hard problem. So we need to find this 0.
You overthink it, though, alright.
Well, that's why I'm trying to teach you that we look at what are we provided. We're provided the velocity, right? So if I'm looking for the motion, I'm just looking to see where velocity is positive and negative. Now I can clearly see it's negative from here to here, and then it's positive. So I just need to figure out what this point is. So on your calculator, we're going to find this 0. Right, so we plug in. So x squared minus 8 over x plus 1 squared. And I'm just changing the setting so that it's reflected by the same window. Window? Did you ever learn that? Changing the window?
I feel like I did.
Did you guys do change the viewing window?
Yeah.
Okay, you did. I know it's like one of those things where I'm sure you've learned it. What's that? I know. So it's nice when the window's provided, then you just have to change. So it's always listed by your x min and max, and then y minimum and maximum. Okay, so we want to find that 0, right? So second calc, or second trace. How do you not have a line?
Why are we just like Then you just do second, like, find the 0.
Yeah, what's the 0? Did you guys get it? 1.254. Great.
This, like, a Calc pro, like,
Because that's what it is. So you have to understand that on the AP exam, you'll have these type of this would potentially be like a quick multiple choice type question. But what happens is sometimes they give you acceleration, sometimes they give you velocity, sometimes they give you position. So what you do in each case is different. This is a very easy problem.
find it for acceleration.
You would find the area under the curve.
So remember in the last problem I gave you acceleration?
Of that, and
You work backwards. So this one is really straightforward, but you almost don't overthink it because all the other ones we were doing integrals or we were doing derivatives. This one isn't, this is basically, here's what we have, right? I know, I'm gonna like, this is getting to be,
have you tried turning it off and on again?
what was, oh, from to 5.
Minus,
1.254. Anybody else?
Yeah.
Okay, so it's moving. Where is it moving to the left?
From 0 to
1.254, and then it's moving to the right from 1.254 to 5.
Wait, so you said this will be a simple multiple choice question?
Yeah.
So my question is, would it be a calculated multiple choice?
This one would. Yeah, this one would. It's just the fact that they gave you velocity, and they want to make sure that you understand what you're looking for when they give you the velocity graph. If I gave you position, what would you be looking at? You would be looking at the slope of the tangent lines. You would look to see where it's increasing and decreasing, right? And then acceleration, you would look at the area under the curve. So that's what you're doing in each kind of situation. You're looking at each graph differently for the same information, right? So, yeah.
So, do you think on a problem like that we could approximate what point it was, or do they give like?
They might have you do an approximation.
Yeah.
Okay, so let's say from that last example, now we have an initial position at 9. What is the particle's position at 1 second and then at 5 seconds?
Oh, you take the integral of the
Okay,
velocity.
I just wrote new position. So your position at 1 second is going to be your initial plus your displacement. In fact, this is a very significant notation right here. So S of 1 is going to be your initial plus your displacement from 0 to 1. Okay? So that's just a calculator. This is a calculator okay problem. So we have 9 plus, remind me what it was. What is it?
It's minus 8.
So in other words, I don't need to find what my velocity function is. Could you find out what the velocity function is? Yeah, but right, that would be a lot of extra work and not necessary, especially if this is a calculator okay problem. You're just going to integrate from 0 to 1, and then we're going to add that to 9. What do we get?
Got 5.33.
Why not?
Okay.
Okay, so you remember the graph? Look at
Oh.
your graph.
It's negative.
From 0 to 1.254 was below the x-axis, so our particle was moving to the left. So if we start with an initial position of 9,
We minus.
we definitely need to end up with, at 1 second, it has to be smaller than 9. Does that make sense? Wait, what did you get?
You didn't add 9 to it.
No, I mean that's what they're at.
Add 9. Everything.
Okay, what would it say it again? 5.
5.333.
All right, now what's your position? Have 5 seconds. Now, there are 2 ways we could do this. Now that we know the position at 1 second, we could use that and then do the integral. So there are 2 ways we could set this up. You could do s of 1, and then we would do the integral from 1 to 5 of v of t dt, or
So you don't have to divide it, right?
you can start over at the initial.
Would you just
These are the same thing, and I need you to recognize both ways of setting it up, because sometimes there are situations where we don't know the initial position, but maybe we know the position at 1 second, or we know the position at 3 seconds. So as long as we know some position, we can write it this way. So basically, knowing any position here, then you integrate from 1 to 5.
would you
Yeah.
suggest we use the second one in case we mess up on the first one?
Yes, I would say if you know the initial position, I would prefer this one. So use this when you know the initial.
Is that way if you like messed up on the calculation?
Yeah, so again, on the AP, although I will tell you, if this was a free response question, if you messed up this part but reused it here, they wouldn't take off points.
Oh, actually.
Yeah, so they, like your carryover mistake, like they don't take off a second time for it.
So, if you got a
So
different answer,
honestly,
you
it
got
would
an
be fine to use this one or this one, as long as you plugged in this number here, even if this is incorrect.
answer. So as long
plug
as you
it in,
get the
you'll
right
get that.
answer with your wrong number,
Yeah, with your wrong number.
you'll get it right.
Okay. What do we get for this?
44.
44? Exactly? Nice.
What did change?
I know they don't usually come out so nice. All right, is that clear? Does everybody understand that? All right, total consumption. So, integral. With the graph, we know the integral represents the area under the curve. We will actually apply that to application problems where we're going to calculate a net change, right? Or a total accumulation. So basically, when we're given a rate, integrate to find total value, or to find the total. Okay, so here's an example. From 1970 to 1980, the rate of potato consumption in a particular country follows this function. Okay. Millions of bushels per year. The same. It's an actual unit of measure.
But like for a potato, is it like how many potatoes is in a bushel?
So you can look it up. Every year somebody looks it up.
I need to.
This is an actual unit, a bushel.
Wow.
T is measured in years, beginning with 1970. So how many bushels were consumed from the beginning of 1972 to the end of 1973? This is all about just the setup. Everything else you're just going to plug into your calculator.
How much?
It's 50 to 60 net calories.
That's not a number of potatoes.
Well, this is what it's telling me, right?
How much is it?
There's 54 pounds. But how much does a potato? How much does a potato weigh?
8 gallons. I got 8 gallons.
Is that 2 years?
It's 8 gallons.
Okay, so it'll be 2
That's 2 years.
to 4.
What's 54 divided by 0.38?
It's 2 years.
About 142 potatoes.
There you go. I should write that in there.
142.
I think that's the closest we've gotten. How much? 100 and
42.
potatoes. That's amazing. All right, so here's how we have to set it up. If we're beginning in 1970, okay, so this represents the function from 1970 to 1980. So what we have to do is we have to try to match these units, okay? So T, if we're starting, we just want to look at from 1972, the beginning, to the end of 1973. Now, end of 1973 is going to match up with the beginning of 1974. And since that's how we are looking at the years, right, comparing it to when we begin the year. So beginning of 1972 to beginning of 1974, and then it's just use your calculator. So it's just plugging it in. Anybody? How many millions of bushels?
I don't think I get why there's a 4. Because it wasn't 4 years.
Remember,
That's up about 4.
basically you look at 1970. That's your starting point.
Right. So
But I'm not
1970,
necessarily,
1974.
so let's say you have a function that models a certain rate of something. It doesn't matter what that is. Okay? Like it could be anything. It could be the rate that you have a water tank that's leaking water. So if you want to figure out how many gallons have been, like how many gallons you've lost
No, no,
from
it's-
2 to 4 hours, that's where you would use it.
Right.
Okay? So we don't care about from 1970 to 1972. We want to look at specifically from 1972 to 1974.
So you put the actual year.
We put the actual year.
No, because my question is, when it becomes 80, wouldn't it just repeat again? You would add a 1, it would be 12 instead of just 2. Yeah? Never mind. I understand it. Never mind.
So if I was asking from 1975 to 1977, you would put 5 to 7.
As long as the difference is 2 there, does it not matter? Or does it?
You tell me. Does it matter?
I feel like it does, but I can't explain why.
Well, why don't you look at it as a graph?
It does matter.
The time does matter, guys. Do you understand? What does this graph look like? 2.2 plus 1.1 to the t. It's an exponential, right? So 2.2, that's where our horizontal asymptote is. And then it goes like this, right? So this is 1970, right? And then here's 1972 to 1974. Is the area under the curve different from 1972 to 1974 versus from 1970 to 1972? So this is an exponential function, which makes sense that they're just saying that as the years went on, the potato consumption is growing exponentially. So over here at 1978-79 has a much larger consumption than in the beginning years. Make sense? So I use the example of, let's say you have a water tank that's leaking. Maybe it starts out slow, but maybe the water makes it, maybe gets the hole bigger and more water comes out as time goes on. Does that make sense? So it's important that our units match, reflecting how much time has passed. Okay, what do we get?
7.066.
7.066 million bushels. Yeah, you can figure that part out. How do you figure out how many? So
Okay.
this is so multiply by 1,000,000 and then multiply by.
1,000,003 potatoes. 1,003,000 potatoes.
It's
Right?
not possible.
That's not. It's more.
7
gotta
million
be
from
more.
100.
It's 1,040,370,000.
It's a big number.
It's 1,040,370,000.
Oh, it's 1,000,000,000.
Yeah.
1,003,000.
That's so many.
That's a little bit.
million.
That's a little better.
1,000,000,000.
In one country? Which
I don't know. I took it from the book. Okay.
That's a lot.
No one thing.
I think you need a lot of because if you think about like French fries,
Oh my God.
My
potatoes,
country is.
all of those,
Little big.
little baked potatoes,
Chips.
breakfast hash browns, potato chips. I don't know, guys. All right, last one here. I think this is the last example. Yeah. Okay. Good. I'm tired. Oh, I'm not feeling so well today. I know.
It's not in this case. It's not.
Okay, here's the graph of the velocity.
There's one more afterwards.
All right, what did I give you? I gave you the graph of the velocity. Okay. Now, I just used slightly different words to describe. So when x equals 2, that's when t equals 0. I'm using x for my position function instead of s. So I just want you to get used to, because sometimes the AP exam will use s, and sometimes we'll use x, sometimes they'll use f of x. So where's the particle at the end of the trip?
Back at its initial point.
Okay, how do you figure out the final position, basically? Right, so remember, this was a velocity graph.
But, okay, so, if I.
Okay, so this is what I'm talking about, guys. You need to look at each problem differently. And so this one is velocity. If I want to know where I am at the end of the trip, what do I need? I need to have the initial plus the displacement, right?
Would you start, from, like, would you ignore the first two, like, and start from 2 to 6? Are we just doing area under the curve?
Yes. So I have 2 plus the integral from 0 to 10.
Why would it be 0 to 10 though, the position starts at 2? At t equals 0, wouldn't it be from 2 to 10?
I want to find my position at 10 seconds.
Okay. Oh,
So
never mind.
this is x of 0, that's my initial, plus my displacement. Displacement, if I write it out this way, it's the integral from 0 to 10 of v of t dt. If I have my velocity, notice I don't have an actual function to integrate this time, so I have to go back to what does the integral mean? It means the area under the curve. Now, do I count the area that goes below as a negative?
Yes.
Yes, it's important. So I have 2 plus, well, let's see, what's this area here? I don't care how you figure it out, just, you want to do a trapezoid?
7. 2 plus 5.
1/2 times the height, base 1 is 6, base 2 is 3. It doesn't matter. And then actually the next one's going to be minus. And it's 1/2, the base is 4, the height is 2. What do we get for the result? So 2 plus 9 is 11. Minus 4. We get 7. Okay. Okay, how about total distance? Right, so I want the absolute value of v of t dt. So that means, do I care about the 2 second, or the 2 position in the beginning? No. I just want to make sure I have this area was an area of 9. This was 4. So I want to add those two. and we get 13. Yes. Yeah. So I'll just assign you like AP practice for homework. And then I do, sometimes there's like group work, because I'll have like groups present free response questions. It'll be more like that. And pretty much if you do your job, everybody gets like 100% on those. So
We go in test category, right?
they actually go into a quiz category. So you'll see. Because it's not so straightforward. It's not like I could just give you a quiz. I do sometimes give like multiple choice quizzes, but I still grade partial credit and all of that, because if I just graded right or wrong, it wouldn't really help your grade. So it's true. It's so hard. You saw on this multiple choice that you did for homework, it's so easy to pick the wrong answer. And that's on purpose. Okay, I forgot. There's one more problem on here. So this is actually a good example where you have a pump. Okay, you have a table of values here connected to a generator. Operates at a varying rate, okay, depending on how much power is being drawn from the generator. Okay, so the rate gallons per minute at which the pump operates is recorded at 10-minute intervals for 1 hour. How many gallons were pumped during that hour? So we've actually done this before, and I gave you a little hint. It just says use trapezoidal rule. And the bases are the same, which is really nice for trapezoidal rule, because otherwise you'd have to set them up as separate trapezoids. So what's that look like? So 10 over 2, and then the first one and the last one are used once, and all the ones in the middle are used twice. So 58 plus 2 times 65 plus another 58. And then plus 63 at the end. So plug that all in. Notice the units are the same this time, so we're good. This is measured in minutes, and this is gallons per minute. So if this was like gallons per hour or something like that, we would have to change it. 3,575 gallons. Perfect.